Hello friends, I welcome you in lecture number 12 on complex integral. In this lecture also we are going to discuss one more variety of problem on contour integrals. So let's start with this problem. Here we are asked to evaluate this contour integral where function is pi times e to the power pi z bar, and this contour C is the boundary of the square with vertices at the points 0, 1, 1 plus I and I, and we have to consider the direction is counterclockwise direction. It is given that the orientation of contour C being in the counterclockwise direction. So first we have to draw this square whose boundary is given, and we have to integrate along that boundary of the square with given vertices. So we roughly try to sketch that square in xy plane. Suppose these are real and imaginary axes. Vertices are at 0. Then suppose this much distance is 1 on x-axis. Suppose this much distance is 1 on y-axis. Then approximately this point is 1 1 or 1 plus I. So we are asked to integrate along the boundary of this square. We are given the vertices, so we have to integrate along this boundary with these vertices 0 1 1 plus I and I. This distance is 1 on y-axis, so this point is ordered pair 0 1, or we can write it as I. I means order pair 0 1, and this is order pair 1 1, and we have to consider starting with 0. We will consider counterclockwise direction, so we have to integrate along this contour. So our contour is the boundary of this square with these four vertices, and we can see now we have four line segments or sides of this square, and along each side we have different equations. If we consider this line segment along x-axis, then we know that along x-axis y is 0, so this will be represented by y equal to 0, and x is from 0 to 1. So here we can write that equation is y equal to 0, x lies between 0 and 1. Similarly, along this boundary or this line segment, x becomes constant. Value of x at any point on this line segment is 1, and y is from 0 to y equal to 1. This point is ordered pair 1 comma 1. This we can write as order pair 1 comma 0. So at this point y is 0, at this point y is 1, so here we consider y from 0 to 1. Then we move in this direction because we have to go in counterclockwise direction, and at every point on this line segment y has value 1, so this we can write as y equal to 1, and we are going in this direction, so x will be from 1 to 0. At this point value of x is 1, at this point value of x is 0, so we will consider limits of x from 1 to 0 when we integrate along this line segment. After that we move in this direction, that is along this boundary. This boundary is on y-axis, so here we write x equal to 0, and at this point y is 1, at this point y is 0, so here y varies from y equal to 1 to y equal to 0, and we can give names to these different contours. We can denote this by C1. Suppose this boundary is denoted by C2, this boundary is denoted by C3, and this boundary is denoted by C4. Then given contour can be written as C1 plus C2 plus C3 plus C4, or you can write as a union also. So integral along C will be equal to integral along C1 plus integral along C2 plus integral along C3 plus integral along C4. So we have to integrate along C1, C2, C3, C4, and then we will add their integrals or their values. And function is pi times exponential of pi into conjugate of z. So first we denote given function by f of z. Let f of z is pi times e to the power pi into z bar, and then we first integrate along C1. So first we integrate along each boundary and then we will take their sum. So along contour C1, along this contour we have y equal to 0 and x varies from 0 to 1. So here equation is y equal to 0, x is from 0 to 1. So y becomes constant and x is varying. So we will convert our function in terms of x. We will take y equal to 0 in the function. So for that, first we start with z equal to x plus iy, and we can write y equal to 0. So we will have z equal to x, and therefore dz will be equal to dx. And f of z, in f of z, first we put z equal to x plus iy. We have e raised to pi and z bar. Z we consider as x plus iy and its conjugate. So our function is e raised to pi into conjugate of x plus iy is x minus iy, and then we put y equal to 0. So we will have pi times e raised to pi into x and minus 0. X minus 0 is x. So our function becomes pi into e raised to pi x along contour C1, and we will replace dz by dx, and limits of x are from 0 to 1. So therefore integral of given function along this boundary C1 is equal to, here x is from 0 to 1, f of z is pi times e raised to pi x, dz is dx. So we have converted our integral in the variable x. Integral of e raised to pi x is e raised to pi x divided by coefficient of x, which is pi, and x is from 0 to 1. Pi will get cancelled, and if I take x equal to 1, here I will have e raised to pi, and for x equal to 0 I will have e raised to 0, that is 1. So this is integral along the first boundary, which is y equal to 0 and x lies between 0 and 1. So in this way we obtain integrals along C2, C3, C4, and then we will add them. So therefore integral of f of z along C1 is e to the power pi minus 1. Now we integrate along C2. Along second boundary C2, along C2 x is 1 and y varies from 0 to 1. We have written here that along C2 x becomes 1 and y is varying. So now we will have everything in terms of y, because x becomes constant. So first we put x equal to 1 in z equal to x plus iy. Let z equal to x plus iy, then z equal to, if I take x equal to 1, I will have z equal to 1 plus iy. Therefore we can write derivative of z with respect to y, that is 0 plus I, and this becomes I. Therefore dz becomes dy. We will replace dz by dy, and f of z is pi into e raised to pi into z bar, and if we take z equal to x plus iy, we have pi into e raised to pi, conjugate of x plus iy is x minus iy, and along C2 we have to write x equal to 1. So here we put x equal to 1, and we have e raised to pi into 1 minus iy, and we can further rewrite this as e raised to pi e raised to pi. Let me write one more step, pi minus I into pi into y, and this I can rewrite as this is e raised to pi times e raised to minus I into pi into y. Okay, using rule of exponent, we know that e raised to z1 plus z2 can be rewritten as e raised to z1 times e raised to z2. So here we consider z1 equal to pi and z2 equal to minus I pi y. So this is our function along C2, and dz is dy and y varies from 0 to 1. Therefore integral of f of z along C2 becomes, here we have everything in terms of y varies from 0 to 1, f of z is pi times e raised to pi times e raised to minus I into pi into y, and dz is dy, and this is now this quantity is independent of y, that we can take outside. Integral is e raised to minus I pi y divided by coefficient of y, that is minus I times pi, and limits of y are from 0 to 1. And now we can see this pi will get cancelled, and we can write this minus 1 by I outside. We have this e raised to pi also, and we can write one more step, e raised to minus I pi y integral from 0 to 1, and this is now minus e raised to pi divided by I, and if I take y equal to 1, here I have minus e raised to I into pi minus e raised to 0, that is 1. And now if I write this minus 1, we can write as I square. So I square divided by I, that is going to be I, and e raised to pi, and this we keep as it is, e raised to minus pi I minus 1. So this is integral along C2 of given function. Similarly, we integrate along C3, along contour C3, we have x equal to 1, and no, this is y equal to 1, and x is starting from 1 and going up to 0. So that we can see here also in the figure. We have along C3 y becomes constant at every point on C3. Value of y is 1, and because we are going in this direction, we will start with x equal to 1 and we will go up to x equal to 0. So along C3 we put y equal to 1. So along C3 z is x plus iy, and we put y equal to 1. So we have x plus I, and if we differentiate with respect to x, we have dz by dx equal to derivative of x is 1, and this is constant, its derivative is 0. Therefore we will replace dz by dx. Similarly, we write f of z in terms of x. F of z is e raised to minus pi into z bar, and if we take z equal to x plus iy, z bar is x minus iy, and here now we have to put y equal to 1. So here I write e raised to pi x is as it is, and we consider y equal to 1 here, and this we can rewrite as e raised to pi x minus pi into I, and this again we can rewrite as e raised to pi into x into e raised to minus pi into I. Using this rule of exponential function, e raised to z1 plus z2 equal to e raised to z1 times e raised to z2, with z1 equal to pi x, z2 equal to e raised to z2 equal to minus pi I, and this I can rewrite as pi e raised to minus pi I, this is constant, times e raised to pi x. Therefore we have written f of z in terms of x only, and now we can integrate along C3. F of z is, here we have to be careful, lower limit of y is 1 and upper limit is 0. F of z is pi e raised to minus pi I e raised to pi x, dz is dx. So we have taken dz equal to dx. X is from 1 to 0. Here our function is of x, so these are the limits of x, and f of z is pi e raised to minus pi a e raised to pi x, and we can first write down integral. This quantity is constant. Integral is e raised to pi x divided by pi, and integral from x equal to 1 to x equal to 0. Here coefficient of x is pi, therefore we have divided by pi. This is independent of x, therefore I have written it outside. This pi will get cancelled, it is constant, and here I have e raised to minus pi I. For x equal to 0 I will have e raised to 0, and for x equal to 1 I will have e raised to pi. E raised to 0 is 1, so we have e raised to minus pi I 1 minus e raised to pi, or this I can again rewrite as e raised to minus pi I and 1 minus e raised to pi. So I am removing this bracket. Let me write in this form. This is integral of f of z along C3, and finally we have to integrate along this C4, that is along the y-axis, and we have along y-axis x equal to 0 and y is from 1 to 0. Now we are on the last boundary of square. Here we have, now we are going in this direction, and along this line segment x becomes constant, x is 0 at every point on this line segment, and we are starting with this point. Here y is 1 and here y is 0, so we consider limits of y from 1 to 0, so that we will write here y is from 1 to 0, and therefore z becomes, z is x plus iy, x is 0, therefore z equal to iy, and therefore dz by dy is I, and therefore dz will be replaced by I times dy. Similarly, we have to write our function in terms of y. Function is e raised to pi into z bar, and therefore e raised to pi z bar is conjugate of x plus iy, that is x minus iy, and x is 0, therefore we have e raised to pi 0 minus iy, that is minus iy, and this is pi e raised to minus pi I y, and finally we integrate f of z along C4. So now our variable is y, and limits of y are from y equal to 1 to 0. F of z is pi e raised to minus pi iy, that we have written, and dz is I times dy. I times dy here, and integral is this pi I constant, and here integral will be e raised to pi I as it is, e raised to minus pi I y divided by coefficient of y, that is minus pi into I. Limits of y will be from y equal to 1 to y equal to 0, and we can see this pi I will get cancelled, and let me write one more step. Here limits are from y equal to 1 to 0, and finally we put y equal to 0, that is we have minus e raised to 0 minus minus plus e raised to y equal to 1 will give us e raised to minus pi into I. And now we can write this first, e raised to minus pi I, e raised to 0 is 1, so this is minus 1. So this is integral of f of z along C4. So along C4 we have e raised to minus pi I minus 1. Now we can use Euler's formula here that we have not used in earlier part also. Whenever we have e raised to I into something, we can replace it by cos theta plus I sin theta. So let me check again. Here I am having integral along C1 equal to e raised to pi minus 1. So that is fine, we will keep this as it is. But whenever we have this type of terms, e raised to I theta, we can use this Euler's formula and we can further simplify it. E raised to I theta can be written as cos theta plus I sin theta. Along C2 we have integrated along C2, but I think here I have dz by dy equal to I, so dz will be I times dy. So I have made this mistake here. I have to multiply with I with dy here. So let me multiply with I, so that I will have I here, and this I will get cancelled, so I will not have this I anymore. So let me cancel this I, and I will be left with e raised to pi times e raised to minus pi I minus 1. And we can further simplify this. I can use that Euler's formula. I can use this I raised to I theta is cos theta plus I sin theta. Here instead of theta I have minus pi, so I can put theta equal to minus pi, and I will have cosine of minus pi plus I sin of minus pi. Cos is even function, so cos of minus theta is cos theta, and sine is odd function, so we have sine of minus pi equal to minus sine pi, and we know that cos pi is minus 1, sine pi is 0, so this becomes minus 1. So here I can take e raised to minus pi I directly as minus 1, and I will have minus 1, that is minus 2 times e raised to pi. And here you can see because we cancel this I, we will not have this I, so we will have negative sign as it is here. So here I have negative sign as it is, so this is negative of this, and negative negative positive, because I had written 1 upon I equal to minus I, but I gets cancelled here, so I can write this as minus e raised to pi, and this I is not there because I had written this I by mistake. I had used 1 upon I equal to minus I, but I is not there, therefore this minus sign is there. So we have minus e raised to pi, this quantity is minus 1, so minus 1 minus 2 into minus 1, that is 2 times e raised to pi. So whenever we have this type of quantity in our integrals, we can use this Euler's formula and we can further simplify. Similarly, let me check whether I am getting that type of quantity anywhere in other integrals. So here also I am getting e raised to minus pi I, so that we can write here e raised to minus pi I we have obtained as minus 1, e raised to minus pi I we can directly write cos pi minus I sin pi. Cos pi is minus 1, sin pi is 0, so this I can replace by minus 1, and I have 1 minus e raised to pi, and I can take minus sign inside the bracket, and I will have e raised to pi minus 1. And along C4 here also we have e raised to minus pi I, So now I write directly minus 1 minus 1, that is minus 2. So once we obtain integrals along all the boundaries, we can add them. Therefore integral along the whole boundary of this square is equal to integral of f of z along c1 plus integral of f of z along c2 plus integral of f of z along c3 and integral of f of z along c4. So we now add all those integrals. Integral along c1 was, let me check again, integral along c1 is e raised to pi minus 1, and first we write integral along c1, that is e raised to pi minus 1 plus integral along c2, that is 2 times e raised to pi. So we write integral along c2 as 2 times e raised to pi, and integral along c3 is e raised to pi minus 1, so plus e raised to pi minus 1, and integral along c4 is minus 2. So here I write minus 2, and you can see here I have e raised to pi minus 1 2 times, that I can write in this way, and from this I can take 2 common, and I will have 2 times e raised to pi minus 1. So we can see 2 times e raised to pi minus 1 plus 2 times e raised to pi minus 1, that becomes 4 times in the bracket e raised to pi minus 1. So this is another nice example on contour integrals, and we have many calculative part here, so we have to be careful, otherwise we will get wrong answer. Here I forgot to multiply with I, and I get another integral answer for integral along c2, but we have to be careful when we have this type of more calculations, otherwise things are easy. We have to integrate along each line segment, which is the boundary of the square with given vertices, and after integrating along each boundary we will add integrals along each boundary, and we will obtain integral along the whole boundary of the given square. So this is all about this session. I hope you like it. Thanks for watching.